Hello everyone, welcome to one more lecture on Fundamentals of Logic. In this lecture video, we'll be discussing about quantifiers. That is, what is an open statement, what is quantifiers, types of quantifiers, and problems based on the quantifiers. So first, let me discuss about open statement. A declarative statement will be called as an open statement if it is satisfied the following condition. The first condition is if it contains one or more variable. And also the open statement is not a statement, but it becomes statement when the variables in it are replaced by certain allowable choices. Example, the number x plus 2 is an even integer is denoted by p of x. Then negation p of x may be reads as the number x plus 2 is not an even integer. Quantifiers. The words like all, every, some, there exist are associated with the idea of quantity. So such words will be called as an quantifier. So for example, if a statement contains the variables like all, every, some, there exist. So these kind of quantities will be called as an quantifiers. So there are mainly two types of quantifiers. First one is universal quantifiers and second one is existential quantifiers. So first we'll discuss about universal quantifiers. The symbol for all has been used to denote the phrases like for all and for every, and in the mathematical logic we'll be calling this as for each and for any are also taken up to the equivalent to this. So these equivalent phrases will be called as an universal quantifier. So the quantities like for all, for every, in logic for each, for any, so these kind of quantities will be called as an universal quantifiers. Second one is existential quantifiers. The symbol they exist has been used to denote the phrases like there exist for some, for at least one. So each of these quantities phrases is called the existential quantifier. So the quantities like there exist for some and for at least one. So these kind of quantities will be called as an existential quantifiers. Example, first one, for every integer x square is a non-negative integer. There exists x belongs to some set x s p of x. Okay, for the universal of all the integers, so let me tell that p of x, if x is greater than 0, q of x is equal to x is an even, rx is x is a perfect square, s of x where x is a divisible by 3, t of x where x is a divisible by 7. So these kind of quantities will be called as a quantifiers example. So some rules employed in finding the truth values based on the quantifiers. The rule 1, the statement for all x belongs to S, p of x is true only when p of x is true for each x belongs to S. Rule number 2, the statement there exists x belongs to S, p of x is false only when p of x is false for every x belongs to S. Rules of inference, it will be called as a rule 3 of quantifiers. If an open statement p of x is known to be true for all x is an universe S, and if a belongs to S then p of a is true. So this is known as the rule of universal specification. Rule number 4, if an open statement p of x is proved to be true for any arbitrary x chosen from the set S, then the quantified statement for all x belongs to S, p of x is true. This is known as rule of universal generalization. Logical equivalence. The two quantified statements are said to be logically equivalent whenever they have same truth values in all possible situations. The following results are easy to prove here. The first one is for all x, p of x and q of x is equivalent to for all x p of x and for all x q of x. Second one, there exists x, p of x or q of x is equivalent to there exists x p of x or there exists x q of x. Third one, there exists if p of x then q of x is equivalent to there exists x negation p of x or q of x. So these three are some logical equivalent statement in terms of quantifiers. Rule for negation of the quantified statement. Rule number 5. To consider the negation of a quantified statement, change the quantifier from universal to existential. So here, after applying the negation for the quantified statement, we'll be getting the universal statement into an existential statement. For example, that is, a negation of for all x p of x will be equivalent to there exists negation p of x. Similarly, a negation of there exists p of x will be equivalent to for all x negation p of x. Problem number 1. Consider the open statement with a set of real numbers as the universe. So p of x for mod x is greater than 3, q of x is greater than 3. So find the truth versus the statement for all x if p of x then q of x. Also, write down the converse, inverse and the contrapositive of the statement and find their truth values. Solution. So, from the given problem we can note that, for example, they have given that p of x is equal to mod x is greater than 3 and q of x is equal to x is greater than 3. So suppose if I take the value of x is equal to minus 4, so I'll be getting what? P of minus 4 is equivalent to modulus of minus 4, which is greater than 3. Yeah, it is obviously true. And q of minus 4 is equal to minus 4 is greater than 3. This is a false statement. So what we can say that thus the p of x, if p of x then q of x is false for x is equal to minus 4. So for this case, the values for x is equal to minus 4, the given equation is not true here. That is, if p of x then q of x is false for x is equal to minus 4. So accordingly, the given statement for all x, if p of x then q of x is false at x is equal to minus 4. So now we'll see the converse of the statement. So I'm going to rewrite the statement number 1 in terms of converse. So what I can write? For all x, if q of x then p of x. I'll be calling this one as equation number 2. So in words, it will be read like, for every real number x, x is greater than 3, then modulus of x is greater than 3. Or equivalently, we can call this one as, for every real number greater than 3 as its absolute values greater than 3. So this statement will be obviously true. Since it is false here, this value is false and this is true. So hence the false tend to true will be a true statement. So it will be a true statement, we can conclude. So next we will find the inverse. So to find the inverse, I am going to apply the negation for the equation number 1. So the inverse of the statement number 1 is given by, for all x, negation of p of x, if negation of p of x, then negation of q of x. I will be calling this one as equation number 3. In words, this reads as, for every real number x, if mod x is less than or equal to 3, then x is less than or equal to 3. Or equivalently, if the magnitude of the real number is less than or equal to 3, then the number is less than or equal to 3. So since I am applying negation here, the greater than is converted into less than here. So since the converse and inverse of a conditional are logically equivalent, then the statements equation number 2 and equation number 3 have the same truth values. So it is obviously true since the two statements, the converse and inverse, are logically equivalent here. So hence we can conclude that the third statement is a true statement. So next is the contrapositive one. The contrapositive of 1 is given like, for all x, negation q of x, if negation q of x then negation p of x. I'll be calling this one as equation number 4. So in words it will be read like, for every real number which is less than or equal to 3 has its magnitude less than or equal to 3. So next is problem number 2. Let p of x is equal to x square minus 7x plus 10 and q of x is given like x square minus 2x minus 3. So and Rx is given like x is less than 0. So determine the truth or falsity of the following statements. When the universe U contains only the integers 2 and 5, and if a statement is false, provide the counter example or explanation. So if the statement is false here, so we have to provide a counter example with explanation. The first statement is, for all x, if p of x then negation of r of x. Second one is, for all x, if q of x then r of x. Third one is, there exists x, if q of x then r of x. Fourth one is there exists x if p of x then r of x. So the given that the universe is given like u is equal to 2 comma 5. So the u contains only two values, that is 2 comma 5 here. And we have to note that the equation x square minus 7x plus 10. So after expanding this and simplifying, I'll be getting x minus 5 and x minus 2. So therefore p of x is true for x is equal to 5, x is equal to, and x is equal to 2. That is p of x is true for all x belongs to u. Because the values 2 and 5, it is contained in the universe u here. Further, x square minus 2x minus 3 is equal to x minus 3 x plus 1. So therefore q of x is only true for x is equal to 3 and x is equal to minus 1. But since here x is equal to 3 and x is equal to minus 1 is not in the given universe u is equal to 2 comma 5. So hence we can conclude that q of x is false for all of x belongs to u. Obviously, r of x is false for all x belongs to u. Now, I want to prove the truth and falsity of the following statements. So, accordingly, since p of x is true for all x belongs to u and negation r of x is true for all x belongs to u, then the statement for all x, if p of x then negation r of x is obviously true. Next one, since q of x is false for all x belongs to u and r of x is false for all x belongs to u, then the statement for all x, if q of x then r of x is obviously true. Third one, since q of x and r of x are false for x is equal to 2, the statement there exists if q of x then r of x is true, obviously it is true. Next one, since p of x is true for all x belongs to u but r of x is false for all x belongs to u, then the statement if p of x then q of x is false for all x belongs to u, consequently there exists x if p of x then r of x is a false statement here. Thank you.